Hey guys, so our project is called Accelerating NASA Science and Engineering through the Application of AI, and it's by me, Munisa, Sean, Sai, Harsha, and William. So, what are we solving and why it matters? We looked at how NASA struggles to deal with the tons of sensors during the deep space mission, and the issue is that there is a big delay in communication and not much human involvement. So, if a sensor messes up, no one might catch it in time, and that could risk the whole mission. So let's look at the system overview, and it divides into main components as a data ingestion, pre-processing, AI modeling, model evaluation, and user dashboard. And on here, you guys can see the chart that I have uploaded.
And that leads us to the integration strategy overview. On the right-hand side, it shows the feedback loop a little bit clearer. It shows a feedback loop going from the AI model to the model evaluation and back to the AI model and then back to the model evaluation. This allows retraining and improvement in the AI. Now, we have some key features. It's modular, real-time anomaly detection, and supports EDS and HPC deployments. It also needs to be scalable and interoperability. So it has containerized microservices with Kubernetes orchestration and NASA standard formats and APIs. The outcome of having key features and scalability is it accelerates AI adoption, improves mission resilience, and enables real-time autonomous decision making in deep space missions.
So for the model specifications, we have the purpose of our model. The first thing we'll talk about is data ingestion, which is gathering in the data and prioritizing it in real time. And then for pre-processing, we're going to clean and normalize the data with annotating the multi-source data compatibility with AI models. For the AI modeling, we're going to develop, and deploy the machine learning models that we use to detect anomalies from the data. And for the evaluation and feedback, we will monitor the performance, integrate user feedback, and retain models if needed. And we'll also provide the mission teams with a user interface, basically an intuitive dashboard for tracking and having insights. For the potential biases that could be in the model for data ingestion, we may overlook low probability but critical anomalies. For pre-processing, we could have poor implementation that could lead to the model drifting or potentially having false positives. For AI modeling, we could overfit because of the data as being too old and using historical data. Some of the models could trade accuracy for speed also. For evaluation and feedback, feedback loops can reinforce users' bias and introduce annotation noise. And for the user interface, it could be a misinterpretation by the people who are not experts on the actual machine learning model. And for the implementation, when it comes to the data ingestion, we'll have APIs for DAAC/Earth data and NetCDF or /FITS support and a heuristic prioritization. For pre-processing, we use Python, Pandas, and NumPy. That's really a common practice when it comes to data and cleaning data with Python. We can use clustering and KNN and Z-score detection also. For the AI modeling, we could use RapidMiner, TensorFlow, PyTorch for optimizing quantization and pruning, and for evaluation and feedback, real-time dashboards, drift detection and version control, consensus-based feedback handling, or we can also and for user interface, we'll have interactive visuals, parameter tuning, and API-based reporting.
Coming to the revealed features, our intelligent data prioritization system addresses the fundamental challenges of limited communication window during deep space missions. Unlike traditional systems, our transmit data based on the fixed schedules. Our approach uses machine learning to dynamically rank telemetry data by anomaly likelihood. This means that during those brief communication windows, the most critical data gets transmitted first. The system continuously adapts its prioritization based on the detected patterns, ensuring that potentially anomalies reading received bandwidth allocation, while routine measurements can be summarized or transmitted later. This is particularly crucial for missions like Europa Lander, where communication opportunities are scarce and unpredictable. Our second key innovation is our hybrid architecture that combines transformer networks with reinforcement learning. The transformer component excels at identifying complex relationship between the different sensor streams and temporal patterns across extended mission timelines. Meanwhile, the reinforcement learning component optimizes decision making based on the mission objectives and feedbacks. What makes this approach powerful is its transfer learning capabilities. A system can be pre-trained on historical mission data that then quickly adapt to new mission patterns with minimal retraining. As the mission progresses, the model continuously learns and evolves, suggesting detection thresholds based on the operational context. This hybrid approach allows us to detect suitable anomalies that might escape traditional rule based systems. Finally, our system incorporates digital twin technology for continuous model validation and improvement. Our digital twin provides a simulation based baseline for real-time anomaly comparison. This gives mission controllers a virtual testing environment for predictive diagnostics without risking actual hardware. As the spacecraft encounters new environments, the digital twin update to maintain an accurate reference model. Perhaps most importantly, our system supports automated feedback loops when mission specialists automate, annotate, or correct model outputs. These annotation feedback into the training cycle, enhancing model accuracy through the mission lifetime. The system includes various controls for model iterations with automated performance tracking and rollback of capabilities if needed. This human in the loop approach balances autonomous operation with expert guidance, making it ideal for the complex evolving conditions for deep space environment.
Now coming to feature directions and exciting features. 1. Autonomous fault response system. Extend anomaly detection to trigger autonomous correction protocols. Self-evolving digital twin. Deploy AI-powered digital twins that evolve with real-time data, enabling continuous mission simulation and predictive diagnostics. Explainable AI. Integrate explainability layers into the model interface for better transparency and trust in AI decisions. Cross machine learning framework. Create a repository of pre-trained models and anomaly patterns that can transfer learning across different missions. Edge AI model store. Establish a cloud sync model repository allowing spacecraft to select update models autonomously based on operation needs. Thank you.